and we can learn and understand how these individuals physically interact with each other. So this concept of human-robot-human interaction is not very new. One of the first example was almost 20 years ago with this study where there was a rotary actuator with two nodes, and two users are in contact with these two nodes while this actuator is being controlled. And at the same time, these two users were trying to track a target that is shown on these monitors. And this was one of the first examples of human-robot-human interaction. And this idea gained much more traction, I would say, in the last 10 years, where we have seen many more studies which mostly have a similar structure, including two robots. And these two robots are programmed such that, for example, in this case, these robots render a virtual spring between the hands of these two individuals, and through this virtual rendering, these two users feel repulsion forces towards each other. And here in these studies, it was mostly in the context of motor control. While having this physical interaction, these two individuals were trying to achieve a task. For example, reaching this dynamic target or moving on this 8 shape. And one of the common results of these studies is that these individuals actually perform the task better when they are physically interacting with each other compared to the condition that there is no interaction. So in this human-robot-human interaction scheme, quite promising results are obtained in the context of motor control, showing the benefit of physical interaction that's improving motor capabilities. However, all of these previous studies are focusing on upper limb studies, and the interaction is only between the single arm of the user, so only focusing on unimanual. And all of these studies are designed in a quite controlled environment, lab environments, with no focus on safety, even though physically interacting with humans requires quite some safety considerations. And even though these experimentations were done in the context of motor control, they were all focused on healthy individuals, and they were not used in rehabilitation settings. But on the other hand, for example, rehabilitation settings are one of the key examples where we see a fundamental physical human-human interaction. For example, here we have a conventional gait therapy happening, where a physical therapist is physically interacting through their upper limbs to the patient leg to assist and correct their gait cycle. So to improve this interaction, and our idea is to use robots, particularly lower limb exoskeletons, for both patients and the therapist, so that we can render this virtual interaction between them immediately through the legs of the therapist and through the legs of the patient, and they can feel each other. So if we can have such a system, we can allow multi-degrees of freedom, multi-contact, and two-legged interaction, simultaneous interaction between the therapist and patient. And for example, here you can see the therapist is only interacting with the single leg of the patient. If an assist is required on the two legs, usually two physical therapists are needed. But however, such a system would allow interaction with two legs simultaneously. And such a system, because of those reasons, could potentially lead to a more efficient interaction between the therapist and patient. And more importantly, we can still use the therapist's knowledge and expertise in this area. At the same time, like harmonizing these knowledge and expertise with the force exertion capabilities and assistance capabilities of the exoskeleton. So the focus of this talk and the studies that I will be showing is about developing the safe physical human-robot-human interaction scheme and verifying this scheme on a gait therapy application. Towards this goal, I will show several studies. First, I will start with interaction force control of a single lower limb exoskeleton. And then I will show how we can use this interaction force controllers of each exoskeleton to actually virtually couple these two exoskeletons together in a bilateral teleoperation sense. How we can include safety for these physical human-robot-human interaction. And at the end, I will show our newly proposed a gait therapy methodology that we called immersive gait therapy that includes that was verified on post-stroke patients and a professional physical therapist. So I will start with interaction force control of a single robot. By the way, if you have any questions, please feel free to interrupt at any time. And before starting with the details of the interaction force control, I would like to emphasize that we are focusing on interaction force control because to have this virtual coupling between these two robots, first it is required that we can properly control the interaction forces between the human and the robot for a single exoskeleton. And first, let me quickly introduce the hardware that we used. We used a Fourier Intelligence X2 exoskeleton. Maybe you are aware of Fourier Intelligence now. They are more towards the humanoid robot production, but previously they were also having this lower limb exoskeletons. So with this lower limb exoskeleton, we have 4 active degrees of freedom, 2 on the hip and 2 on the knees, and we have an IMU on the backpack so that we can have the orientation of each link with respect to the gravity. And we developed a custom open source software with multiple layers that allow us to control different exoskeletons and different robotic systems that use CAN Open Communication Protocol. Without getting into too much detail, it consists of 3 main layers, with lower layer handling the communication protocol details, and the highest layer where we are implementing our overall logic and control strategies. And to be able to control this robot, one of the important thing is to have proper system identification of this robot. So we achieve this by giving some torque profiles, kind of random torque profiles, and measuring the resultant outcome of the links. And with using that data, we fit like mass, center of mass, and inertia parameters together with the friction coefficients, which is quite significant for this robot. So after having the software infrastructure and properly identifying the robot, we were able to tackle the interaction force controller. And this robotic hardware comes with some challenges, especially in terms of controlling these interaction forces between human and the robot. First of all, the first main challenge is that measuring these interaction forces between human and the robot. This is mostly due to the fact that there are many contact points happening. There are several contacts at the foot plates. We have contact happening on the cuffs. We have contacts at the trunk on this backpack. And it's not really feasible to implement here 6 degrees of freedom force torque sensors to each contact point. Additionally, we are having forces due to the ground reaction, and we should be able to distinguish the forces due to the ground reaction forces and the forces due to the human interaction. So instead of using force torque sensors at each contact point, we implemented strain gauges at the output of each joint so that we can measure the joint torques, and indirectly through the use of these joint torque measurements, indirectly calculate the interaction forces happening between human and the robot. Another main challenge is that this robot is quite heavy. It's more than 20 kilograms. So it is very critical that we compensate the whole body weight of this exoskeleton. So the users must not feel this heavy weight, and the weight, the exoskeleton should compensate all of its weight and should transfer the weight into the ground in a proper and continuous manner. However, state-of-the-art lower limb exoskeleton models usually models the legs separately, which is feasible for lightweight exoskeletons, but is not usable in our case with a quite heavy exoskeleton. Another challenge is the control of hybrid dynamics due to the contacts happening from the ground due to the heel strikes or toe-off events that change the dynamics instantaneously. So we tackled these 3 main challenges mostly through our modeling approaches, where during single stance, we modeled the exoskeleton as a 4-joint 5-link system, where the ankle, we assume the ankle is hinged to the ground. And we are using the whole body model. So we are using both left leg, right leg, and the backpack component into our model with this hinge assumption on the ankle. And of course, this model depends on the stance leg. So for a left stance, we will have a different gravity vector. And for right stance, we have a parallel model where we have the assumption this time that the right ankle is actually hinged to the ground. So this one is quite straightforward, a very simple model. But the main tricky part is how to handle the model during double stance. So how to handle this transition from left stance to right stance, which includes double stance includes around 20% of the gait cycle. So during double stance, we use our knowledge of the ground reaction forces due to the sensors at the foot plate. And we use these force measurements, or more correctly, the ratio of these force measurements to have an interpolation factor that gives us a clue of how close we are to the left stance or how close we are to the right stance. For example, if the vertical forces are 90% on the left leg and 10% on the right leg, we have an interpolation factor of 90% saying our system is 90% closer to the left stance. And we use this interpolation factor to smoothly transition between these different dynamical parameters corresponding to left stance and right stance. So this interpolation factor changes with respect to the weight, and the weights changes continuously during the whole gate cycle. So we can have this smooth interpolation factor during the whole gate cycle that allows us to have this quite smooth continuous model. And after having this model for different gate states and different transition periods, I would like to show the interaction force controller that we have implemented. So we have a desired interaction force value, which can change based on the task that I will show in the next slides. And we compare this desired interaction torque with our estimation of the interaction torque, which gives us the interaction torque error, which is fed into an admittance controller, includes only a virtual mass. And this admittance outputs a desired joint acceleration. So we have an admittance controller at the acceleration level. And this desired joint accelerations are fed into a constraint optimization scheme where we use our equation of motion, the model that I showed in the previous slide, together with physical limits of the system to calculate the motor torques that would achieve these joint accelerations as best as possible under the given physical limits. And we also use this model to estimate the interaction torques between a human and the robot by simply subtracting the gravity component that depends on the gate state from our joint torque measurements. And usually the first approach to test any kind of interaction force controller is to first test the transparency of it. So having a zero desired interaction force. So here I would like to show some results. So when the desired interaction force is zero, we call this as haptic transparency. So the robot is trying to minimize the forces between human and the robot. So the user is free to move without any predefined designed trajectory, and the robot should follow the user. So here you can see, even though this is quite bulky, more than 20 kilograms of exoskeleton, I can quite easily move with the robot, so leading the robot without any predefined trajectory, climbing stairs, or moving both forward and backwards, both on the ramps, stairs, and overground. And here, one really nice feature of this controller is that controller has no knowledge of the terrain. Here, the robot does not know if it's a ramp, what's the inclination angle, if it's a stair, if it's overground. That information is not known, but our generalized like weight compensation and modeling approach allow us to handle these together, of course, with our knowledge of the orientation of every link with respect to gravity to handle all of these different terrains. So this is good to show the first performance of the force controller in terms of haptic transparency. But just having zero interaction force, it doesn't make much sense in practical sense. We actually want to give some force to the user to assist them for some towards some specific for some specific manners. So therefore, we also tested this interaction force controller for non-zero desired interactions. Here we have virtual spring and dampers connected to a fixed location at the hip and knee of the user. And here these virtual spring and dampers resulted in a desired interaction torque between a human and the robot. And these are shown with blue, and the measured interaction torques are shown by red. So here again, user is moving without any predefined trajectory, but feeling these forces pushing the joints towards these desired points, and feeling these forces due to the accurate force controller that we have implemented. So after having interaction force controller of a single robot, so now we have the ability to apply different forces to the both limbs of the user. The next step is to actually virtually couple these two robots in a bilateral teleoperation sense, so that these both two users can feel each other. So this is called dyadic interaction, with like dyadic implying there are two people interacting with each other. So we have this interaction torque controllers that I have shown separately, independently running for each of the robots. And we have another third node, a virtual coupling node, that is responsible of rendering some virtual interaction medium between these two individuals. So this virtual coupling node receives the robot state at every time instant, and depending on the properties of this interaction medium, calculates the desired interaction force for each robot, and then outputs these desired interaction to individual torque controllers. And in terms of this virtual interaction medium, this virtual coupling between them, we have investigated different approaches, such as joint space interaction, where we render virtual spring and dampers between the hip and knees of these users in the joint space. Or we can also implement this virtual interaction in the task space, for example, having this virtual interaction medium, for example, between the ankle of these users, or even their trunk or center of mass of these exoskeletons. So I would like to show some videos demonstrating this coupling. So here there is no coupling between the users. The commanded interaction torques are 0. And here on the left, you are seeing the joint angles, blue for user A on the left and yellow for user B on the right. So here they can freely move without feeling any forces. So basically it's haptically transparent. But once we enable, for example, a strong coupling between the hip and knees of these users, this time, for example, here we have some strong spring and damper elements between them. This resulted in a non-zero interaction torque in opposite directions for both of these users, so that their joints are pushed towards each other. And this results in a quite synchronized motion between them. And whenever there is some deviation between their joints, it results in a high interaction torque that push their joints back. And we tested this interaction while walking. So here we have two users walking on a treadmill while having their exoskeletons. And what we did is, while they are walking, without letting them know, we changed the interaction stiffness between these two users. So first, we let them walk without any connection between them, so having zero stiffness between them. And without letting them know, we adjusted the stiffness, the stiffness of this virtual interaction medium between them. And as expected, we observed that their kinematics get closer. So here you can see their hip angle of both users getting closer as we increase the coupling strength between them. And we also tested this in a teacher-student scenario, where here, this time teacher tries to teach a new gait pattern to the students. So here we have a student with user B and teacher with user A. And the student has no knowledge of this new trajectory. And the teacher is seeing this new desired trajectory on the monitor and trying to teach that to the user only haptically. Here, it's not visible on the image, but the student was not able to see the teacher, so the student is only feeling the forces and no knowledge of this new gait trajectory. And this new gait trajectory was an asymmetric gait trajectory, where we have more knee flexion on the left leg compared to the right leg. And even though the student had no knowledge of this, the teacher was able to communicate this new trajectory only through this virtual physical coupling between these exoskeleton to the student. We also tested this interaction at the task level for a sit-to-stand task, where we have this time this interaction between the center of mass of these two users. For this sit-to-stand task, these two users on their monitor receives a desired like center of mass height, and they are trying to reach this center of mass height by basically like squatting up and down. And this is one of quite useful cases to have this physical interaction, because you can imagine, for example, a stronger peer here can help a weaker peer on the other side by through like just following a similar trajectory, just sitting and standing up to provide that support to the other side. And in this study, we also observed similar results to the previous one, where we saw that tracking of this task was improved when they have this interaction between them. So they were actually tracking worse when there is no interaction between them, and when they are actually working together in a coupled manner, they were able to track these targets better. And similarly, as we increased the stiffness of this interaction, their accuracy of tracking also increased. So now I have showed them interaction force controller for a single exoskeleton and how we actually create these virtual couplings between these two exoskeletons. But these comes with also some challenges in terms of the safety aspects. So it is quite critical that both on the hardware side and software side, the ability to implement different safety criteria, also depending on the user that is wearing the exoskeleton. As you can imagine, different patients can have different safety requirements. So in terms of these safety constraints, we had considered several different of them. The first of them is physical limits of the exoskeleton. For example, we would like to limit the power transmitted to the user through the actuators. we want to limit the motor torques at any time. And more importantly, we want to limit the joint positions in a safe region that can also change depending on the participant's needs. For example, we would never want this knee to go for hyperflexion or hyperextension. Another important aspect is because we are using this on a walking task, it is quite important that we can achieve some balancing constraints, also like both for walking and a sit to stand task. And we should be able to have these safety constraints while tracking this desired acceleration or desired forces coming from the other user. So we achieve that by expressing these constraints and these tracking tasks by defining them as either as equality or inequality task and solving them from starting from the highest priority to lowest priority without compromising the optimized solution of the higher priority task. For example, having this joint torque limit is a more priority task than being able to track the desired force. So these safety constraints have a higher priority in these task definition than force tracking capabilities. And we solve this through the use of a sequential quadratic programming, where we define these tasks in a sequential manner. And here, okay, I cannot play this video, but here we are, even though the user here wants to move further away from these trapezoidal defined region, the robots push the user back into this constraint region so that the center of mass is always inside the support polygon and the user won't tip over. So after having this coupling between them and ensuring we have some safety implementations for different users, like building on top of all these three main areas of studies, we developed and proposed this new gait therapy, which we call as immersive gait therapy, where we have this therapist, robot, and patient interaction. Before going into the details, I would like to go back to one of the initial slides to remind these limitations of conventional gait therapy. So here, the physical therapist only has a constant interaction medium, which is like they can, of course, change a little bit the impedance through their arms, but the palm interaction stiffness of the palm is quite pretty much a constant. The physical therapist is mostly having a single contact point with the leg. For one therapist, it's not possible to interact with the two legs at the same time. In a hospital, when they need assistance on both sides, usually there is two therapists at the same time, or one therapist is switching sides. And this is upper limb to lower limb interaction. When we were discussing with professional physical therapists, they mentioned that this interaction is not straightforward and quite a learning curve, especially for the new physical therapists, like understanding where the leg is, adjusting how to move your hand based on that. From our feedback, we understand that this is not a very straightforward task also for the physical therapist. So for these reasons, we have developed this gait therapy method, where here we have the, let me turn the voice down. So here we have the therapist and here a post-stroke patient, both wearing exoskeletons. And here they are facing each other, looking in the different directions. And here we are having this interaction between the left leg of the therapist and the right leg of the patient. This is, we inspired this from conventional gait therapy, where most of the times there is a mirror in front of the patient so that they can see themselves and they can coordinate. So here we are having like kind of this mirror, but this time on the back of the mirror, it's not the patient itself, it's the therapist. And here we have this coupling between the both legs of the therapist and the patient. And we have asymmetric spring and damper between the hip and knee joints of the therapist and the patient. And the therapist has the ability to change the stiffness of this interaction on the go, on real time, based on the needs of the patient. For example, if therapist needs, they need to show emotion in a more strict manner. For example, they can increase the stiffness that's affecting the patient and then show that motion without receiving too much resistance from the patient. And while having this virtual physical interaction between the therapist and patient, they can also see each other and also verbally interact with each other, as in the conventional gait therapy. So we compared this proposed immersive gait therapy with conventional gait therapy, where in the conventional gait therapy, the physical therapist just conducts conventional gait training without having any robotic systems, just with their hands. And we have the immersive gait training that I just showed. So we enrolled 8 post-stroke patients and a single professional physical therapist. So we had the same physical therapist for all post-stroke patients and for both training. And we asked these post-stroke patients to have a visit twice, one for the dyadic training, this immersive gait training, and the other one is for conventional gait training. And the order of their visit were, of course, randomized for different patients. And the training protocol for both of these cases included 3 sessions, 3 10-minute sessions, and in between the sessions, a break amount decided by the patient, decided by the therapist, considering the needs of the patient. But it was mostly changing between 1 to 5 minutes for each 10-minute training sessions. And during these sessions, we have measured the kinematics of the patient, the effort that the patient providing, and the motivation. So we want basically better gait kinematics for the patient. However, we want to achieve better gait kinematics, not just due to the effect of the therapist, not just due to the forces that therapist is applying. We also want to see high effort from the patient while achieving these better kinematics. This is critical because if the patient is not putting any effort, and if only the therapist is driving the patient, this won't result in, like after the training, the effect of the training won't be seen. It won't be longitudinal. So here, I would like to quickly show the kinematics measurements that we have obtained. You can see here for 8 users, for 3 sessions, their vertical ankle position with the vertical axis and horizontal ankle position on the horizontal axis, while blue is the dyadic. So this immersive gait therapy, and the red is the conventional gait therapy, where we obtained a larger step length and higher foot clearance with this newly proposed immersive gait training. And this better kinematics was not only due to the force that the therapist was applying, it was also due to the effort that the patients were giving. So here we have the muscle activation for 3 sessions and for different participants, representing by each dot, and the mean for the dyadic case and the conventional case are shown by these horizontal bars, where we obtain almost for all users higher muscle activation compared to the conventional gait therapy. So in summary, we obtained better kinematics during training with this dyadic immersive gait therapy while achieving higher training efforts. I didn't show, but we also had a subjective questionnaire where we measured their motivation and enjoyment during these training sessions, and they had a very similar motivation, quite high motivation and enjoyment for both of the conditions. And we also received quite good also like informal feedback from them, where they mentioned, some of them mentioned like their knees have never been that high. They thought that it was like dancing with the therapist due to this virtual forces that they are feeling between each other. Let me skip this. So in summary, today I have mainly showed 4 main studies that builds on top the latest study that I showed. First, I've gone through this interaction force control of a single robot. Then using this interaction force controller of a single robot, we have this bilateral teleoperation or this virtual coupling between these 2 exoskeletons. And we have a framework that we can implement different safety conditions, and building on top of these studies, we